Hello everybody and welcome to my 40th video now. This is on a base N SR flip-flop. I'll be going through the design process for designing an SR flip-flop in any base, as the name suggests. So first we'll start off with a definition. AM equals 1 if A is greater or equal to M, 0 otherwise. So here we have the binary case. This is A1 because there only is A1 in binary and it's the same as A, so A1 equals A. So this is the SR flip-flop. This is the truth table for the SR flip-flop using the NAND configuration. This is a circuit diagram and you invert the inputs S and R to get Q and not Q on the output of the SR flip-flop. Technically you don't need Schmitt triggers in there, they just need to be inverters, but just shows you the basic circuit diagram. I'll be using this as a basis for a base N circuit. Right, so these are S and R, input set and reset, Q the outputs, SR Q and not Q, and basically you set a 0 from S equals 0 to R equals 1, and set a 1 to S equals 1 and R equals 0, and a 1 1 is a prohibited state. So the idea is you set the 0 or the 1 and then you get it to the whole state, which is Q, which is S equals 0 and R equals 0. So yeah, that's the binary case. So this is the ternary case. Here we have A. This is A2, 0, 0, 1 in response to 0, 1, 2, and this is A1, 0, 1, 1 in response to 0, 1, 2. These are the S and the R and the Q outputs from, variables for the ternary SR flip-flop. And this is S1 and S2 for S according to this truth table here. This is R1 and R2 for R according to this truth table here, and Q2 has inputs S2 and R1, which is there, and Q1 has inputs S1 and R2. Now the idea is to set a logic state either 0, 1 or 2 and get it to the whole state Q, which is S equals 0 and R equals 0. So for example, to set a 2, you got set S to 2 and R to 0. R is already a 0, so you just need to get S to a 0. So a 1, 0, S equals 1 and R equals 0 holds a 1 or a 2. So a 2 is held, and 0, 0 is the whole state, holds a 2. That's an example. For 1, you can either set R to a 0 first and hold a 1, or S to a 0 first and hold a 1, and then S equals 0, R equals 0 is the whole state. So that's the basic design for the ternary SR flip-flop. This is the circuit diagram, well, the simplified circuit diagram, just showing the SR configuration with the NAND configuration. So Q2 has inputs S2 and R1, this is Q2 here, not Q2, has inputs S2 and R1, and Q1 has inputs S1 and R2, this is Q1, S1 and R2. The full circuit diagram can be found in my video, Binary Implemented Ternary Logic Circuits. So this is the basic layout for the ternary SR flip-flop. Right, this is the Quaternary SR flip-flop. Again, I'm using a coding for AM. A equals 0, 1, 2, 3. A3 equals 0, 0, 0, 1 in response to 0, 1, 2, 3. A2 equals 0, 0, 1, 1 in response to 0, 1, 2, 3. And A1 equals 0, 1, 1, 1 in response to 0, 1, 2, 3. So here we have the quaternary inputs SR and Q, and these are S1, R2 and R3 for R, R1, R2 and R3 for R, S1, S2 and S3 for S, and Q follows this truth table here. Q3 is S3 and R1, S3 and R1, Q2 is S2 and R2, S2 and R2, and Q1 is S1 and R3, so S1 and R3. Again, the idea is to set the logic state 0, 2, 1, 0, 1, 2 or 3, and for example, if you set a logic 3, 3, 0, S is, or R is already a 0, so you just have to get 3 to the hold state, which is 0, 0. So 3 goes to a 2 there, 2, 0 holds a 3, S goes to a 1, 0 holds a 3, and then you get S equals 0 and R equals 0, which is a hold state, which holds a 3. Similarly for the 2 and the 1 and the 0 logic state, however you do it, you always end up holding the logic state. For example, Q equals 0, 3 goes to 2 goes to 1 goes to 0 to the hold state. So these intermediate states hold a 0 for Q, to go to Q. S equals 0, R equals 0. Right. So this is the circuit diagram for the quaternary SR flip-flop. So Q3 has inputs S3 and R1, Q2 has inputs S2 and R2, Q1 has inputs S1 and R3. So this is Q3 and not Q3, Q2 not Q2, Q1 not Q1. So Q3 has inputs S3 and R1, Q2 has inputs S2 and R2, Q1 has inputs S1 and R3. So a full circuit diagram can be found. I've got a quaternary video on it with the SR and D type flip-flop. This is just the basic circuit to show the NAND configuration SRs, binary SRs. And right, yeah, a full circuit. So that's the quaternary version. So here we have a quinary version, base 5, A equals 0, 1, 2 and 3 and 4, A4 equals 0, 0, 0, 1, A3 equals 0, 0, 0, 1, 1, A2 equals 0, 0, 1, 1, 1, A1 equals 0, 1, 1, 1, 1. Now, these are the inputs S and R to the flip-flop and the output Q, and R1, R2, R3, R4 for R, coded according to this truth table here. S1, S2, S3 and R4 are for S, coded according to this truth table here. Now Q4 has inputs S4 and R1. This is S4 and R1. Q3 has inputs S3 and R2. So S3 and R2. Q2 has inputs S2 and R3. S2, R3. And Q1 has inputs S1 and R4. So the idea again is to set your logic state 0, 1, 2, 3 or 4, and then get it down to the whole state Q, which is S equals 0, R equals 0. So the easiest one to see here is setting a logic 4. So S equals 4 and R equals 0. So R already equals a 0, so you just need to get the 4 down to 0 for the whole state here. 0, S equals 0, R equals 0. So 3, 0 holds a 4, 2, 0 holds a 4, 1, 0 holds a 4, then down to 0, S equals 0, R equals 0, which is the hold state. So we can go on to the haven't done the circuit diagram for this. We'll just have a summary. For the binary case, Q1 has inputs S1 and R1. So A1 equals A, therefore Q has inputs S and R. That's the binary NAND configuration. Ternary, Q2 has inputs S2 and R1. Q1 has inputs S1 and R2. That's the binary NAND configuration again. Quaternary has Q3 has inputs S3 and R1. Q2 has inputs S2 and R2, and Q1 has inputs S1 and R3. And for quaternary, Q4 has inputs S4 and R1. Q3, I say quaternary, it's quinary. Q4 has inputs S4 and R1. Q3 has inputs S3 and R2. Q2 has inputs S2 and R1. Q1 has inputs S1 and R4. So in the general case, base N, QM has inputs S, M and R brackets N minus M. So M equals 1, 2 to N minus 1. So if you want to build a base N flip-flop, you just use the NAND configuration, the binary NAND configuration, and let the inputs for QM equal SM and R N minus M. Right, I think that concludes the video. I'd just like to say thanks for watching. Hope you've enjoyed it. Bye.